Okay, let's get started. So my name is Yuxian. I'm an assistant professor in CS, and I lead the Intelligent Robotics and Vision Lab. So welcome to today's CS Mixture for faculty and PhD students. And I will give you an introduction to model-based robot manipulation. So if you don't know about robot manipulation, today is a good opportunity to learn about how can we do robot manipulation. So the goal of our lab is to build intelligent robots that can help people in various environments. So we hope in the future we'll have robots that can take care of our senior citizens, assist disabled people, or serve people in various places. So in the future, we hope to have robots that can cook a meal, clean a kitchen table, or load the dishwasher for you at home. So that's the dream of the research in our lab. From these examples, you can see one common thing of these robots is about manipulation. Right? For robots to perform these tasks, they need to manipulate objects or use objects to perform some tasks. So that's why when building intelligent robots, manipulation is a very important problem, and it is also a very challenging problem. So today, my focus is mainly on model-based robot manipulation. This is a traditional pipeline where people attack manipulation problems. So usually we have this perception, planning, and control pipeline in this model-based approach. And particularly for model-based robot manipulation, in perception, we can tackle this problem called 60 object pose estimation. So given input image, you can detect objects and then estimate the 60 pose of objects. Here, 60 pose means 3D rotation and 3D translation. If you know 60 pose, basically you mean how far the object is from the camera and what's the orientation of the object is from the camera. And this information can be used in the second stage of the pipeline. It is planning. So then we can do grasp planning. That is to plan how can the robot gripper grasp objects, and the motion planning. It is about how can the robot arm move a motion, generate a trajectory to reach one of the grasps. So for example, we can have this 3D model of objects in the planning scene and plan a trajectory of the robots to grasp one of the objects. So this is the planning stage. Once you have a plan, in the end, we can do the control. So the control here is basically following the trajectory generated by the planner. So in this example, the front arm, the robot arm will follow the trajectory and eventually pick up the objects. So that's a big picture of model-based robot manipulation. And I will start with perception and introduce some algorithms for 60 object pose estimation. So as you can see from the name, it's called a model-based. Here, model means 3D model of objects. And first of all, how can we get 3D models of objects? There are some techniques we can use to build 3D models of objects. For example, we can use multi-view images. So this is a setup from Berkeley. They have a turning table in the middle, you can see, and then set up these cameras. Then you can capture multiple images of the same objects from different angles. With these images, they can build a 3D model of objects. Here's the example I found online. You can also just use your cell phone and take a video of the objects, then generate a 3D model. Or we can do 3D scanning. There are some 3D scanners you can use to build a 3D model of objects. Basically, these are based on you have some laser and then hit the objects, get the feedback from the laser scan. For example, Google has built a large database called Google Scan Objects. They have used 3D scanning techniques to build thousands of object models. They are free online. You can download for your research. And these are daily objects or some toys they can find online. So it's a database of 3D models. And recently, we have a research project of just use images to build a 3D model of objects. You can see if we use 3D scanner, that's expensive. If you want to set up these multiple cameras, it's also expensive. What if you just have a single camera, but the human manipulate the object in front of the camera? From this video, you generate the 3D model. So this is done by Jikai by using a tool called the bundle steer from NVIDIA. So here's a demonstration. He just manipulates the object in front of the camera, You can see this is the RGBD camera. We have RGB and depth. Then we can use some segmentation techniques such as SAM and XMAM to segment the foreground mask of the objects. And the approach can also estimate the 60 pose of the objects. And from this information, there's some nerve-based technology. They can get a 3D model of the objects. Right? In this case, in this way, it's a cheap method. You just need to shoot the object in front of the camera and get the 3D model. It also can speed up the reconstruction process. But the current limitation is that this approach cannot work well for every object we care in the manipulation setting. It may fail for some objects, and that could be future works to extend. For example, metal objects, when there's a reflectance, or transparent objects, or some object you cannot get very good segmentation or pose, it's hard to reconstruct the shape. Segmentation will be difficult, and also we need to have depth. Some object you cannot get the depth from the camera. That's also difficult. I saw another question. By accuracy, you mean the shape, the accuracy of a shape, or the? Yeah. Oh, this is the after you use the whole video to build a 3D model. I just visualized the 3D model in a mesh lab, isolated. So that's just the build 3D model after the algorithm. Yes, right. So it's not in the beginning. I gradually reconstructed it, right?
The data is rather expensive computationally. So how long of a video does it take, like, for example, train one training model?
The video is about 2,000 frames long, but you want to cover every aspect of the objects. That's why you see first you rotate on the table or grasp it and rotate it. So otherwise there will be some missing parts. But that's a train by using this nerve technology. You can have just use a single camera to build a 3D model. Okay, these are some examples of how do you get a 3D models. Suppose now we have 3D models objects we care about. Then how can we do the 60 object pose estimation? Right here, model based means for this object in the image, we already have 3D models for them, and our goal is to estimate the 60 pose of these objects. So first of all, let's define what's the problem set up here. We're given input image, which is captured from a camera, and we also have the 3D models of these objects. So basically, for each 3D model, we have model coordinates, right? 3D model, you have X, Y, Z. That's the model coordinates or object coordinates defined on the objects. We also have the camera coordinates where the image is taken. So basically 60 pose means that we want to estimate the 3D translation, where's objects in the camera, and also what's the 3D rotation from the object coordinates to the camera coordinates. If you know 3D translation, you know where the object is. If you know the rotation, you know the relative orientation of the objects in the camera, right? So that's the two types of information we can get from 60 object pose estimation. Object position in the camera frame, we use T, that's a 3D translation, and object orientation, that's a 3D rotation matrix, right? Suppose we know 60 pose, given input image, we can visualize these axes in 3D. These are point cloud from the depth camera, and this RGB colored axis means the XYZ axis of the model. You can also project the 3D model to the image. You can see if the 60 pose is accurate, we can overlay the 3D model to the image. So these are the information we can get. There are a lot of applications of using 60 pose estimation. Today we focus on robot manipulation, but you can also imagine augmented reality, right? You can augment Eiffel Tower onto the objects if you can estimate the pose of the objects. Or in the industry object inspection, you can compare the image against your 3D model to know is any part or defect fail for the model, for the objects in the image. So let's focus on the robot manipulation part. So traditionally, how can people solve six object pose? There are two lines of research. The first line is feature matching based methods. You build a 3D model with textures or features onto the 3D model, like in this example. Then give an input image, you can match your image feature to your feature on the 3D model. Then you get this 2D and 3D correspondence. If you get a set of 3D, 2D correspondence, there's some method you can use to compute the 60 pose from this correspondence. So this type of approach is called feature matching based methods. And on the other side, there are template matching based methods. Here, templates, you can generate these templates by rendering the 3D model. Suppose you have a 3D model object, you can render the 3D model according to different views, and these rendered images are templates. In order to detect the object in the image, you can scan your templates like a sliding window fashion in the image, and then localize the objects in the image, and also match the detect object to the templates in order to decide its orientation. So for example, this power drill, you can render a lot of views and then use these views for matching. So these are template matching based methods. So from my early work, we did propose a neural network called the POSE-CNN. It was the first end-to-end 60 pose estimation network. So the network is able to take an input image or input video and then produce 60 pose for all the objects in the video. It can deal with textless objects, symmetric objects, and a kind of occlusion between objects. So for the network architect itself, first you have an input image, then we use a feature extractor to extract features. The first branch of the network is to do semantic segmentation. It's a conv, deconv architecture, then you label each pixel into one of the objects. So the color here means different objects. And in the middle of the network, it's another branch. It's trying to predict, we call this center direction and center distance. So basically for each pixel, you predict a unit length vector pointing towards the object center. So like this map is the x direction of the center direction vector. This is the y direction of the center vector. And this is the z coordinates of the translation. So if you can predict this vector, then you can do a half voting, right? This vector will intersect. Then you find the intersect of these unit directions. That will be the predicted center of the objects. So it's a half voting technology in the middle of the network. And we have a half voting layer. You combine these predicted directions and localize the object center indicated by the yellow dot here. So why we need to have this kind of a voting, right? Why not just predict where the center is? The voting is useful to deal with occlusion. If a certain part of the object is occluded, the visible part can be used to predict the center. So then the technology is it is like a robust to occlusions. So from the center prediction and the center detection, we can estimate a translation and also get a bounding box for each object. So after that, the last branch of the network is you crop the feature of the bounding box and then use some fully connected layers to predict the rotation. So basically the middle branch is to get the translation and the last branch is to get the rotation. Then we can combine the rotation and the translation to obtain the 60 pose of the objects. So you can see the network is end to end. There's a segmentation, translation estimation, and the rotation estimation in the network. Then with this network, here are some results from the POSE-CNN trained for these YCB objects. You can see on the top left, these are detection and segmentation, and the yellow dot indicates the center. And these are the pose predicted from the network. And we also show the colored x-axis in the 3D. So, but you can still see some jittering and the shaking of the pose. That means the network is not very confident. Okay. Then after that, we also introduced another matching network, 60 object pose refinement network called a DPIM. This is a approach you can get a very accurate pose estimation. So the idea is to start with the initial pose estimation. For example, you can get the initial pose estimation from PoseCN or any other pose estimation methods. Then this approach will refine the pose. So suppose we get a pose 0 as our initial pose. We have a 3D model. We can use the initial pose and generate a rendered image. Right, the render will be just a simple OpenGL render. You input a 3D model and then render an image. Then we input the rendered image and the observed image to a network. The network will output a pose. We call it a delta pose, where you can add it to the previous pose to get a new pose estimation. So the network is to predict the refinements of the previous pose. And we get a pose 1. Similarly, we get another rendered image, and then combine the rendered image with the input image and predict another delta pose we can add to the previous pose. So this is the iterative process. At every iteration, you predict a delta pose, then you add it to your previous pose to improve it. And so if the network is trained such that it will gradually match the objects and then get a very accurate pose estimation. There's some follow-up work, for example, cozy pose and the foundation pose just proposed last year. They also use some refinements to improve the pose estimation. But from the numbers you can see compared to PoseCN, if we do DPIM plus PoseCN, the boost is very significant. And here's the demo to show. You can see PoseCN is not very stable, right? But if we do the DPIM refinements, you get a very stable pose estimation. Okay, so this iterative matching is helpful to improve the pose estimation accuracy. After that, we start to think about we can do single image pose estimation. How about pose tracking? If you are given a video, can you track the pose of the objects in a given video? And some traditional approach to do tracking is particle filtering, right? Then we introduce this method called the pose RVPF. It's a black white the particle filter for 60 object pose tracking. So the key component in this method is how to represent the particle, right? When you do particle filtering for localization, the particle indicates the XY location of the robots. But here we have particle to represent the 60 pose of the objects. And the particle has 2 parts, a translation part and the orientation distribution part. That means we try to model the distribution of the orientation. Instead of a commit to a single estimation, it's a distribution of the object pose can be modeled in the method. And the orientation is discretized into about 200K bins. That's a large number of rotation we can model in the network. Then we have particle. How can we compute the likelihood of particle? Right? Particle filtering, basically you sample a lot of particle, you compute the likelihood, then you compute the maximum likelihood estimates, then propagate the particle to the next frame. Yeah, particle here depends on your problem. As I just mentioned, right? If you do robot localization, your particle is the location of the objects. But here, the particle is the 60 pose of the objects. So each particle is, you can think about it as 6 numbers. They represent the pose of the objects. But then we sample a set of particles, that's the status estimation of the objects. So once we have the particle, we have the translation part and the orientation distribution parts. Let's see how can we compute a likelihood of the particle. Once we can get the likelihood, we can do maximum likelihood estimation. Suppose we're given this particle, right? We have the translation part. The translation basically decides the location of the objects in the image. Then we can use the translation to crop a region of interest of the objects. We get an ROI of the objects. Then to compute the likelihood for the orientation distribution, we use an encoder to compute some feature for the cropped ROI. We get some feature representation for the region of interest. And the method maintains a code book that's each view of the rendered image, there's a feature vector. Because we have the 3D model, we can render the 3D model to arbitrary views and then build a code book of the objects. After that, we can compute the similarity between the particle code against the code book and get some histogram, right? If the code is similar to one of the templates, you will have a tick here. That means it's more similar to that rotation. So this is the distribution of the rotations. So we call this rotation likelihood. Then we have the, we can combine the crop of the ROI with the rotation likelihood, so we can get the likelihood for the particle. Then we sample a lot of particle. Each particle has a likelihood. We just use the maximum likelihood estimation of the particle to decide the 60 pose of the objects. So the good thing is you have uncertainty estimation because it's a distribution of the pose, and you can also propagate the particles to do the pose tracking. If you want to know more details, I can check the paper. So here's the demonstration of the tracking. You see the camera is moving, right? But the approach is able to robustly estimate the 60 pose of all these objects in 3D. So it's approach which can track 60 pose and also have some uncertainty estimation of the objects. Okay, any questions for this? If not, I'll sure. Yeah. We use a template matching to compute the rotation likelihood. So we base on template matching, but it has this particle sampling and the particle propagation part inside of the particle filtering framework. Okay, so now let's move to the second part of the model-based manipulation. It's about planning, right? From perception, we obtain the 60 pose of all these objects. Then how can we generate a good plan for grasping or for using the object to do some tasks? In this model-based approach, that means we have 3D model of objects. Then some traditional method, such as GraspIt, is a software you can load the 3D model of the objects, then sample grasps, and then evaluate are these grasps good or not in a simulator. So here's a demonstration generated from Nina. We have these two different grippers. You can see the gripper, the software is trying to sample different grasps and then evaluate is it a successful grasp or failed grasp. So it's a sampling-based approach. You sample a lot of location and then evaluate for each sample location. You have some grasp quality evaluation. Then you see if the quality is high, that's a good grasp. So this is a traditional approach based on sampling. And recently, there are some methods that are based on physics simulation. You can load the objects in a physics simulator and then check if the objects can be successfully grasped in the physics simulator. So for example, this work is using the Flex simulator. You load the objects according to the grasp, then shake it. If the object falls, that means it's a bad grasp. For this master bottle, this green fox indicates the planned successful grasps from the simulator. And recently, we generalized this approach to different grippers. The previous one was just for one single gripper with 2 fingers. So we can try many different grippers with different finger and in the simulator. And this one is using NVIDIA iStack Sim. But in this case, we just close the finger and see will the object fall. If the object falls, that means it's a bad grasp. Then we can filter this bad grasps. But also it depends on you close the gripper and then you measure the time when the object fall. You can have a ranking of this grasp. If a bad grasp, the object will fall immediately. But for some good grasp, the gripper can hold the object for a longer time. So based on the falling time of the objects, we can have a rank for these grasps. So we can use the physics simulator to synthesize a lot of grasps. And with this, we generated a data set, we call it multi-gripper grasp. It's a data set with more than 30 million grasps from 11 grippers. And this gripper has 2 fingers, 3 fingers, 4 fingers, and 5 fingers. One of the gripper is a human hand. And we use 345 objects in the physics simulator to generate these grasps. So this will be a large scale data set with a lot of grippers when you want to do grasp synthesize, right? These days, people use neural networks to generate grasps. Then you can use this data set to do some generating models for grasp synthesis. So another property of this data set is these grippers, they are aligned. So that means if you have a grasp of one gripper, you can transfer that grasp to other grippers. So in this example, we have a source grasps from our fetch robots. So you can see this grasp can be transferred to other grippers. It's also even transferred to the human hand, or you can transfer the grasp from human hand to other robot grippers. So this is a way, hopefully, you can use this data set to learn generalized grasping skills, right? You don't commit to just a single grasp, single gripper. Suppose we learn some grasp synthesize method or grasp policy method, you can apply to all these different grippers. Okay, so this is about the grasp planning parts. With 3D models, we can also use physics simulator to plan grasps of these objects. So lastly, suppose we have a set of grasps. How can the robots generate a trajectory to reach one of the grasps? This is called the motion planning part. The open motion planning library is a well-designed, maintained library for robot motion planning. Once you have the goal location, this library can generate a trajectory to reach the goal. So here's a demonstration. We can use this library combined with 60 object pose estimation. You can see these are the planning things. Once we estimate the 60 pose of objects, we put the CAD model here. That indicates the obstacle. Right, then the robot just, I'll play it again. Then the robot, the motion planning library can generate the trajectory of the robot arm to reach one of the grasps. And the technology behind this is based on RRT, rapidly sampled trace in the configuration space of the robots. So we can also do some trajectory optimization of the robots. And this is a work where we do joint trajectory optimization and the grasp selection. From the grasp planning parts, you can see that for each object, there are multiple grasps. How do you know which grasp should we use? This is a grasp selection problem. Previously, the motion planning and the grasp selection, they are usually separated. Or you can loop over each grasp and see if there's a trajectory to reach the grasp. But then that will be inefficient. So this method called the OMG planner, it can jointly select a grasp and optimize the trajectory of the robots. Here's the illustration. At iteration 0, the green gripper indicates the current grasp that is selected for grasping the objects. So you can see during optimization, the goal will change. So the trajectory optimizer, it will select a better goal to grasp objects. Eventually, it will convert to one of the good grasps to grasp objects. So this is a method where you can do joint motion and grasp planning. All right. And very recently, we introduced another trajectory optimization method called grasping trajectory optimization. The method is use point cloud to represent the objects. So you can see a lot of red points on the robot surface. We sample a lot of red points to represent objects. And also the scene is also represented by point cloud. This green point indicates a point cloud of the scene. Then by computing distance between these red points, you have a way to avoid obstacles. But why we use point cloud is because it's the most generalizable representation, right? For any 3D scene, you can get a depth image and get a point cloud. for any robots, you can sample point cloud on the robots. So ideally, this approach can generalize to any robots and any environments. But for the trajectory optimization, it's a constrained optimization problem. We have an objective function and a set of constraints. So we solve the trajectory. So Q is the trajectory that's from time 1 to time t. And at every time step, you have a configuration of the robots. And the Q dot is the velocity of the trajectory. So basically, we solve both position and the velocity of the trajectory. But for the objective function, this main function here is trying to select one of the grasp. Suppose we have k grasp, we will choose the one which minimize the cost here. And this term is a collision avoidance term, and this one is a regularization term. So for this grasping term, that's we require the robot to reach the grasping goal. We have two goals. One is called the standoff pose, and the other one is called the grasping pose. So this C goal is try to make sure the robot can reach the grasping goal, and this C standoff is trying to make sure the robot can reach the standoff goal. So why we need to have this standoff and the grasping goal is because for some object, if you directly plan to the final grasp, the robot may hit the objects. So if you first go to the standoff, then move to the objects, it's easier for the trajectory planner to generate a collision-free trajectory. Okay, so that's the objective function. Basically, the robot should reach the goal and avoid obstacles along the way, and with some regularization on the velocity. So the constraint is basically it's start from the initial configuration of the robots. In the beginning, there shouldn't be any velocity, like q1 dot is 0. In the end, there shouldn't be any velocity, like qt dot is 0 too. And this constraint is the kinematics, basically position plus velocity multiplied delta t should be the next position, right? That's kinematics of the robots. Then for position qt, there's some joint limits, lower bound and upper bound. For the velocity, there's also a lower bound and upper bound. So then we set up this constrained optimization problem. Just use an external solver to solve it. Once you solve it, you get a trajectory of the robots to reach one of the goal. So here's a sure. Oh, regularization is for the velocity, right? You don't want the robots to generate a large velocity. It will either dangerous or it's gonna be consume a lot of energy, right? And here's a demonstration. Because we use a point cloud representation, we don't need to have a 3D model for the shelf, right? You just need to have a depth image. Then this boundary of the shelf, these are obstacles. You shouldn't touch them. So that's why the point cloud representation is more general. Then here in a simulator, we can have these robots to pick up this object from the shelf. So it's a trajectory optimization method to reach one of the grasps. We also tried experiments in the real world. We put a shelf in the lab, put the two objects in the shelf. First of all, there's some perception. This is from Jinshinu, right? It's a grounding dyno for detection and grounding stem, and the stem for segmentation. So you get the segmentation mask of the objects. Then we can have the point cloud of the objects. Then by doing the trajectory optimization, we can generate a trajectory of the robots to grasp these objects. Okay, so that's the planning part. Basically, we can tackle the grasp planning and the motion planning. Then let's recap of this picture again, right? We have the perception, planning, and the control. Control just follow the trajectory. And some interesting result is before I came here at the NVIDIA lab, we can have the robots to open cabinets and grasp object from the cabinets. the perception part is pose estimation for the handle. So you can see from the top, we also have the handle detection. And then after the robots open the cabinet, there's a trajectory planner, plan a trajectory to grasp the sugar box and put it on the table. So the story is that even this model-based approach, they are limited to certain models. It's still useful in some constrained environments. Okay. So for the last part of my talk, I will talk about benchmarking. So if you work on machine learning or computer vision and natural language processing, there are a lot of benchmarks you can use for experiments. But in robotics, it's really hard to build benchmarks because everyone's lab is different. You cannot have the same setup, the same robots to do the same testing. So benchmarking is a problem in robotics. For 6-object pose estimation, there's a very good benchmark called the BOP benchmark for 6-object pose estimation. They have a common data set for training and testing, and they organize challenges. People can upload their results to evaluate. Then they maintain a leaderboard of 6-object pose estimation. So if you're interested in 6-object pose, you can check the BOP challenge or BOP benchmark. But go back to benchmarking in robotics, there are some efforts. So the first line of effort is to use simulation, right? If you use simulation to evaluate, everyone can use the same simulator, same robots. So then we call it's reproducible, right? Everyone can share the same test environments. Then it's a fair comparison. But to test in the real world, it's not that easy to generate the same testing thing, to generate the same reproducible things for testing. There's some efforts. If you check the thing reproducibility here, we already have 4 methods that is reproducible. The first one is from NIST. This is assembly tasks. So they basically design this board for assembly. The robots need to place these parts to the holes in the board. Because every team can use the same assembly board, it's a fair test and it's a reproducible test case. For general things, if you want to build the same testing things, people sometimes use these markers. You place the markers in the thing, then you can make sure you place the objects every time it's the same location. So we can use these markers to create reproducible things. For example, this one, the grasp plot. They print this marker board, then every time they place these objects, they place on the same location. So it's a fair test case for the robots. But what we introduced is a new benchmark called Scene Replica. In this case, you don't need to use any markers. You can naturally place objects onto the table, and then we have a mechanism to make sure you can place the object in the same location. Then we create a fair test case for the robots. So let's see how can we build this benchmark with the efforts with several students in the lab. So we start with this 16 YCP objects. These are widely used for robot manipulation. First, we want to know how to place them. Then we can use some algorithm to compute stable poses of these objects. So these are poses where the object can be placed stably. We call them stable pose. Some examples are shown here. Then, in order to place the objects, we need to also know which location the robot is reachable. So we can test the reachability of the robots in a simulation. There's these blue blocks indicate the robot can reach that location. Then we can place these objects on these blue dot locations, make sure the robot can reach. So with this design, we can generate a set of robot object configurations on the tabletop by some sampling strategy. So in the end, we generated 20 things for the fetch robots, and these are the things we can use for testing. So you can see from these examples, We have different object configuration, different clutter, and different occlusion between these objects. So we use this as reference things. Every time we want to do the grasping, we can place the objects according to these generated images. But how can we make sure it's reproducible? So here's a demonstration. When we place the objects, we overlay the reference image to the live view of the robot camera. Then you can visually align the objects to the reference image to make sure you place the objects according to the reference image. Right. With this visualization and the interface, every test we can place the objects exactly in the same way. So then we can make sure it's a reproducible thing for testing real robots. Okay, so that's our idea of how to create reproducible things without using any markers, basically overlay the reference image. With this data set, first of all, we benchmark the model-based grasping. I will recap how can we do this model-based grasping. First of all, is you do 60 object pose estimation of the objects. And then for each object, we assume you have some grasps, either from grasp it or some grasp planner. Now, with the grasp, we can do a motion planning to reach one of the grasp. And finally, the robot can grasp, lift the objects, and drop it to the other side. So this is a pipeline we use to benchmark model-based grasping. So here's a video to demonstrate the model-based grasping with scene replica. So the 60 pose estimation method is called GDRMPP. It was last year's best method for the BOP challenge. And then the grasps are generated from grasp it and with some top-down grasping. And move it is used for motion planning. With the setup, we count the success rate of grasping, like in 100 grasps, how many are success, and how many grasps you can move the object to the other side. So this is a pick and place success. Then we did a lot of experiments, compare different perception method and planning method, cross planning methods, and motion planning methods. So we can maintain a leaderboard of all these methods. So you can see on the top is the best 60 object pose estimation methods, and with grasp it and the move it for motion planning. The success rate is not that high if you want robots to work in your home. It's like 66 success among 100. That means just 66% success rate for pick and place. So there's still a large room to improve. Okay, that means there are still 34 failures, right? Then let's take a look at what are the typical failures by doing these experiments on our benchmark. The first failure is from perception. So sometimes the object detector, it cannot detect the objects. For example, the ball is in the middle of the table, and the object detector we use, it's a yellow trend on these YCP objects. It cannot detect this ball sometimes. But I assume better perception, better detector will solve this problem. Another failure case is about grasping failure. So let's check this example. The robot is trying to grasp the banana, but it's going so deep, then the finger hit the table. So when it lifts, it cannot grasp the banana. Then this failure is due to the grasping failure. And another common failure is about the pose estimation error. In this video, the robot trying to grasp the power drill. You see, it directly poke into the body of the power drill. It's because the pose estimation is wrong. Then the robot cannot pick it up. So better pose estimation can also increase the the success rate of the grasping. Okay, so these are the 3 typical types of failures from our benchmarking experiments. Any questions? Okay. Uh-huh. Yeah, because this is a testing on the same set of robots, same set of objects, but we provided the purchase link of these objects. You can order them from like Amazon. So, right, in order to achieve reproducibility, you need to use the same objects and place them in the same location for testing. That's a good point. Yeah. For class, this is called a deformable objects manipulation. There also a line work focusing on this. So, but the method is still trying to figure out, for example, which corner to grasp for the class, right? You need to figure out the grasping points and then pick up the class or manipulate the class. There are some approach on that too. But here it's still rigid objects. We're focusing on the model-based approach. Okay. So then that's all I prepared today. In conclusion, let's recap what we have talked about so far, right? I basically introduced this pipeline of model-based manipulation. It has a perception part, the 60 object pose estimation. In planning, you need to do grasp planning and motion planning. Grasp planning is to figure out where the gripper should place to grasp the objects. And the motion planning is how to reach the planned grasp. And the control, we didn't talk too much about control because we just use existing software, make sure the robot follows the trajectory. So the pros of the model-based approach, it's suitable for controlled environments where you can get these 3D models of objects. For example, industry setup. If the application only care about certain parts of some machine, right, you can easily get the 3D model or CAD model of these objects. It can be useful for this kind of controlled environments with 3D models. Another benefit is you can generate synthetic data for manipulation with 3D models. For example, the grasp planning, you need to have a 3D model in the simulator to generate the grasps for learning, right? You can use this asset to generate synthetic data or learning from simulation. If you want to learn some policy or learn some manipulation skills in simulation, you need to have these assets. So then the model-based method, you can have this 3D model in the simulation to generate data for learning. But the cons of the model-based approach, it's first of all, it's very straightforward. It cannot handle unseen objects, right? You need to have model for objects in order to manipulate. But what if the robot is given a completely new object? How do you manipulate it? So that's one limitation of the model-based approach. And for the grasping, it's also limited by the performance of the sixth object pose estimation. Although compared to early days, the accuracy is significantly improved, there's still errors from this pose estimation. If the pose is wrong, no matter how you plan, right, you will fail to grasp objects. So that's the limitation of this approach. Okay, so that's all, and thank you so much. I can not present this without the effort from the student in the lab. So if you have any question, I'm happy to answer that. Okay, thank you. Thank you so much. Any questions you want to know? If not, oh, here. Uh-huh.
So we solve, or we have some solution.